In this case, we're trying to show how the hill slope here, which is this curve here, is just a profile down a hill. So our coordinate system is h is elevation, x is distance along the profile. How we can kind of what's behind the idealization that the sediment transport, the motion of material down the hill, is basically proportional to local slope. And so delta h over delta x is that local slope. K is the constant proportionality, and here we have a minus sign because if you think about it, as we go over in x, we're going down in h, so this is a negative slope. So it just means a positive sediment transport in a negative slope. It's just for convenience. But the basic idea is that if you have things like tree throw, a burrowing animal, in general, the more material is going to go downhill than uphill, and the steeper the slope is, the more material moves downhill. So we can just plot this rule up, and here I've taken the negative sign out, but we just say that that sediment flux is linearly dependent on the local slope, and so there you see that constant proportionality is the K. So the K kind of gives us a general sense of the vigor of the activity. So low K means that it's not as vigorous for a constant slope as a high one would be, and we might ultimately attribute that to local climate variation, where dry places would have lower rates and maybe wetter places would have higher rates. But it's really important to say this is not runoff driven. It's not rain that's producing runoff and causing rivers. It's just that the wetness will allow for more activity that might include soil creep, these biogenic processes, rain splash, so actually the rain falling and propelling particles, and also for other planets, especially where we might see a lot of meteorites coming in, is meteorite impact.